Assalamu alaikum. So in our series of lectures for mechanics of machines, we are on the topic of balancing. A couple of slides will discuss about some fundamentals. So we will keep going from there. So balancing is a process of correcting or eliminating unwanted inertia forces and moments. So there are two things: unwanted inertia forces and moments in rotating machinery. So first of all, you need to understand balancing is one of the thing which is very crucial for mechanical components, particularly with focus interest or the rotary machining. And what we do, how we do basically balancing by eliminating unwanted inertia. Normally when we refer to inertia means removing the mass. So with that will help also eliminating the inertia forces and moments in a rotating machinery. The shaking force on the frame can vary significantly during a cycle of operation. So even if you have a little bit of shaking force during the normal cyclic operation, this shaking force could be really dangerous actually. Such forces can cause vibrations that at time may reach dangerous amplitude. So you might have a little information about natural frequency. So what happens if you have some component which is rotating, so it's a rotary machinery, and then if you have some unbalanced inertia forces or moments, and if they keep going or with the rotational speed, the frequency of that vibrations can go higher and higher, and if they reach the natural frequency, then it can really cause the catastrophic failure because it reaches a higher dangerous amplitude. Even if they are not dangerous, vibration increase component stress and subject bearing to repeated loads that may cause parts to fail prematurely by fatigue. So you have designed some component because of unwanted balance, unbalancing in the situation, and then it can cause the premature failure of that component. Thus, in design of machinery, it is important. It is not sufficiently merely to avoid operation near the critical speed. We must eliminate or at least reduce the dynamic forces that produce these vibrations in the first place. So this is crucially important when you are designing some component. You have to get rid of all the unbalanced forces. You have to eliminate in first attempt, but if you can't, or at least you have to reduce the effect. So if you reduce, then in fact you are increasing the life of the component. Tolerances used in the manufacture of machinery are typically set as tight as possible without prohibitively increasing the cost of manufacturing. So tolerance is the word actually used when you are manufacturing some machinery part. So you have some plus minus limits. So for example, you are manufacturing some part of with the diameter of 5 millimeter, but the final part would be 5.1 millimeter or 4.9 millimeter. So this 0.1 on each side of 5 mm will be called as a tolerance. So these tolerances used in a manufacturing of machinery are typically set as tight as possible. So if you have a wide range of this tolerance, you have a more problem in the component, especially for the rotating component. So you want to set those tolerances as minimum as possible. So in general, however, it is more economic to produce parts that are not exactly true and then to subject them to a balancing procedure. Then it is produce such perfect parts that no correction is needed. So these two paragraphs, this is very important. So as I said, when you are manufacturing some mechanical part, you have some tolerance in it. As I give an example, you want to design or you want to manufacture some shaft, for example. Again, and you have been given the dimension, some certain dimension. So you manufacture that shaft with a 5 mm and with a tolerance of 0.1, let's say. So the maximum diameter of the shaft could be 5.1 mm, and the minimum diameter of the shaft could be 4.9 mm. So this is the tolerance. So if you want your part to be exactly of your dimensions, you make it at just 5. But mechanically it's very difficult because it involves a lot of machining process, and that machining process also has some tolerances and some uncertainty, and the precision comes in. So you also get to have a very expensive machining process to ensure you are producing the part that is exactly of the same dimension what you need. But of course, if you want that, you are increasing the cost of manufacture. So now it's a trade-off actually. So you don't want to increase cost of production. What you do, you make part with the least cost, and then of course with the least cost it has tolerance. So now the tolerance will cause some kind of unbalancing in the system. So the best practice would be to balance that. So now you see you have two options basically. One, you manufacture part with really tight tolerance, which will be very expensive to make. So you make it, but it will have low unbalancing. So it will be quite balanced. The other option is you make a cheaper part, and it is cost effective, but it has larger tolerance. Then you have to go towards the balancing to make it a balance, and that's the cheaper option basically. So therefore each part produced is an individual case, in that no two parts can normally be expected to require the same corrective measurement. So thus determining the unbalance and the required correction in principal topic is a study of balancing. So the study of balancing really required two-step study. First, you have to determine what is the correction required, right? So determining the unbalance and the required correction. So first you have to determine what unbalancing you have. Remember this when we are doing the balancing some problems in the coming slides. These two steps we will follow. First we will have to find out what are the unbalanced forces in there, and then how to correct. The second step is how to correct that. So figure shows, this is a very fundamental example which was given in the book, this Shigley. So which I thought maybe is very good to introduce here. So figure shows a disc shaft combination resting on a rigid horizontal rails. So this is one of these disc shaft. It has this shaft, and then this is a disc, and it's sitting on two rails, right? So it's a horizontal rails, which is assumed to be perfectly straight, can roll without friction. So this disc can roll without any friction. A reference system XYZ is attached to the disc and move with it. So now what you do, you can mark actually XYZ plane basically. So Z is in the direction of the axis of the shaft, and X and Y, which are mutually perpendicular, they are on the, or they're also marked over there. So now if you, let's say when you roll it, then this XY plane will also roll with it. So simple experiment to determine whether the disc is statically unbalanced, right? So we are interested in finding this, if this disc is statically unbalanced, how you do it actually. So this very simple experiment will help you to establish the fundamental knowledge, what is balance and unbalanced situation actually. So simple experiments to determine whether the disc is statically unbalanced can be conducted as follows. So what are the steps? We can roll the disc gently by hand and permit it to coast until it comes to rest. So you roll it and then wait when it's going to rest. What you do now, then we mark with chalk the lowest point on the periphery of disc. So let's say you roll it and now it is in static condition. So what you do, you mark at the lowest point. So this is the lowest point, let's say. So this is the lowest point. You mark with a chalk over here. Then we mark chalk the lowest point of the periphery of the disk. After we repeat this 4 or 5 times, if the chalk marks are scattered at different locations around the periphery, the disk is in static balance. So what we do, we mark this point, do another turn, and if you have, so after we repeat 4 or 5 times, so this experiment you do 4 or 5 times. So after you have done 4 or 5 times repeat, if the chalk marks are scattered, so scattered means we have marks of chalk somewhere here, somewhere here, so it is getting balance on different positions actually. At different locations around the periphery, the disk is in static balance. So it is called as a static balance. So disk is in static balance. If all of the chalk marks are clustered, so all the chalk marks are just at some point rather than scattered around the periphery, what does it mean then? Which means that the axis of the shaft and the center of the mass of the disk are not coincident. The position of the chalk marks with respect to XY axis indicate the angular location of the unbalanced but not the amount. So where the clustered chalk points will be there, that will be the point which is unbalanced basically. The position of the chalk marks with respect to XY axis indicates the angular location of the unbalanced. Why we are saying the unbalanced? Because you rotate it, it's coming back to the same position. What does it mean? That is the point which is a little bit heavier, right? So if the chalk marks are clustered in here, let's say 4 or 5 chalk marks are here with the 4 or 5 measurements. So what does it mean? The shaft, the disc has more mass over there, so that's why it's getting to that lowest point. So that's why it is called as a unbalanced situation basically. So it is unlikely that any of the marks will be located 100 degree from the remaining cluster. So practically such kind of example, when you are doing practically, you will hardly see that the marks will be located 180 degree from the remaining cluster. So you have one cluster 4 or 5 points closer and one point which is away from that, 180 degree away from that. So let's say what is saying, you have 4 or 5 points over here and one point sitting over here. So it is quite unlikely practically. Although it is theoretically possible to obtain static equilibrium with the unbalance above the shaft axis. So, but theoretically it is possible, which we will do in a couple of slides now, the theoretical calculations. If static unbalance is found to exist, it can be corrected by drilling out. Now, this is the remedy. So you have the static unbalance, you have found it. If static unbalance is found to exist, it can be corrected. What are the options now? By drilling out material at the chalk mark cluster, this is one option. You can do that. So first option, it can be corrected by drilling out the material. What does it mean? You make a hole in the shaft, partial or complete. What you're doing, you're basically removing the material. When you remove material means you are reducing the mass from where the cluster is there, or by adding the periphery 180 from the cluster. Yeah, so option is you found different cluster over here. What you do, first option, you drill from here and remove some material, or else you add some extra mass over here 180 degree apart. So both this mass will be balanced by this mass, then it will be a balance actually. So there are two ways to do that. Since the amount of unbalance is not unknown, the correlation magnitude must be found by trial and error. So in this problem, because we don't know exact location and exact amount of mass to be added or removed, so this is more like a trial and error method to do this balancing, which is quite difficult to do. So that's why we have some systematic calculations which will be introduced this slide and within this lecture, and we'll follow those processes. So by the end of this lecture, we would be able to understand how can we theoretically determine the unbalance in the system, and then how can we correct that. So this is the thing. So you see, this book has very nicely structured this simple experiment to pave a way that if you have a problem in any unbalancing, which you can easily found by doing simple experiment, and then you can correct, but the correction requires little bit extra effort, which in this case is proposed we can do trial and error method, but actually we will develop some knowledge so that we can use that one to find out the corrections, basically to balance the situation. All right, so this is one of the examples of unbalancing. So if an unbalanced disk of shaft M is mounted in a bearing and caused to rotate an angular speed of omega, then an inertia force of magnitude mr omega square. So where rg is the eccentricity, is the distance from the shaft O and the mass center G of the disk as shown in figure. So again here, so this kind of nomenclature normally represented by showing this is a bearing. So this is one bearing, this is another bearing, and this is the axis of rotation, which is basically a shaft. So this is the shaft, right? And this shaft has a disc, and disc is not attached to the shaft at the center, rather it is attached at some eccentricity. So this is the center, which is the center of gravity of the shaft, or mass center. So this is G, is the mass center of the disc. So this disc, if it is connected at G, so if this G point is over here, means if the RG is 0, means the disc is at the shaft. So in that case, we will not have any kind of unbalanced situation, right, in ideal world. But this eccentricity is causing, you can imagine when it's moving with some, so this is angular direction. So when it's moving, so this center of mass, so it's kind of like one mass at a distance rg from the center of rotation. So it will cause a force. What is this force? This force is mr omega square. This is the inertia force. I'm quite sure you are familiar with this formula, which is quite intensively used for measurement of inertia. So this is the inertia force which we use actually. So now you imagine at this particular instant when eccentricity is in this direction, so this is causing, the center of this mass is causing a outward force, which is the inertia force, which is equal to mr omega square. Omega, what is omega? Omega is the angular speed. So this is the net force towards. So how this force is now compensated? This force is compensated, of course, with the bearing, because bearing is the one which has to afford this load. And now if you consider this is the bearing, so you can just, this is like a simply supported beam. So this shaft now is just like a simply supported beam, which is being held at the ends, and it has one of point load acting downward. So when its load is downward and this much load, the force mr omega square, so the bearings has to suffer or has to have the extra loading, right? And this extra loading can be solved very easily by using the principles of simply supported beam with a point load. So this formula is the ratio which comes up. So this is FA. So the part of the force is going towards A, bearing A, the support A, and the part of the one is going with B. So if you are familiar with the bending moment and shear force diagram for the analysis of simply supported beam, you would be very confident doing that. So you got a simply supported beam being held at A and B, and it has a point load mrg omega square inertia force, and you can find out what are the forces at each bearing, right? So B over A plus B, B is this distance, and A plus B is the total length. When you do FB, so this is A, and total length is A plus B. So that's the way you find out the forces. So the figure also shows the force acting on the shaft, that is produces the rotating balance reactions FA and FB. So FA and FB are also given over here. So one more thing over here, this is at some certain instant. Of course, when it's moving, so this load, when it's over here, the shaft in this direction, so it will be somewhere here. So then the force direction will be here. So force is basically changing its direction. So this is a very good example to understand. There are three things which are important to consider here. So one thing, why this RG is here. So this RG, we don't want to produce that one. We want to, for example, if we want this disc to be attached at G, but because there is some eccentricity or the precision of the manufacturing, you manufacture the shaft, it has some tolerance. You manufacture the disc, it has some tolerance. You made a disc and you had center of gravity sitting somewhere over here, right? And then you're attaching, you have the attachment. So net resultant is this one is coming because of the manufacturing process. So manufacturing process is not quite accurate. So that what has resulted in forming this this eccentricity. So when you have this eccentricity, so this is one thing that I was explaining, the eccentricity why is present. So this is now present. Now what is the consequence of this eccentricity? Because it is causing these inertia forces, and when it's moving, so if it's static, it will just stay in this side. But when it's moving, it's even more worse. What is that? You got this force coming in each side. So this point of the shaft, so this point of the shaft is moving in each side basically. So what will happen? So you have to and fro forces, and of course the bearing, when this force is this side, when force is this side, you got your force is this side, you got the bearing force in that side. But when you have inertia force acting in this direction, so the bearing force will be in this direction. Now you imagine if you have a bearing which has this load continually varying, what would happen? This will result in a early failure of the component of the bearing. So that's why this unbalancing causes a intermittent or fatigue loading. Fatigue loading is the one which is changing with the time, and it is well established in literature. The fatigue actually reduces the life of the component. So because of that fatigue, the life of the component will be much less actually. So that's why we really need to get avoid of the unbalancing. All right, then the static balancing machine. Yeah, so it was very interesting machine, one of the very early machine being mentioned in the book, so I thought I could include. So the first purpose of the balancing machine is to indicate whether a mechanical part is in balance or not. So this is the first thing. So I said there are two steps for the balancing. One, you have to find out if there is some unbalance. If it is out of balance, the machine should measure the unbalance by indicating its magnitude and location. So the machine should help you to find out how much balancing you have, how much imbalance you have basically. So static balancing machines are used only for parts whose axial dimensions are small. So this is, we are talking about only static balancing machine, not the dynamic. So these are used only for axial dimensions such as small, such as gears, fans, impellers, and the machines are often called single plane balancer since the mass must lie practically in a single plane. So everything should be in a one plane rather than a multiple planes. So this is the limitation of these kind of balancing machines. So static balancing is essentially a weighing process in which the part is acted upon either by gravity or by inertia forces. So the one I have given an example for the disc on a shaft in a very first slide. That was also one of the way to do the static balancing, and we have to find out by gravity or inertia mass. We have seen that the disc and shaft could be balanced by placing on a parallel axis, rocking it, permitting it to seek equilibrium. That this is the example which I have given you for the shaft, the disc, the first page. In this case, the location of the unbalance is determined through the force of gravity. Another method of balancing the disc is to rotate it and predetermined speed. So you rotate the disc at some certain speed. Then the bearing reaction can be measured. And then you find the bearing reaction, what's happening in the bearing, and their magnitude used to indicate the amount of unbalance. So you rotate. So for example, with continuation of this one, so you got some unbalance, you rotate it and you read the reaction forces, or you measure the reaction forces at the bearings. So the magnitude here will give you how much inertia force you have in the system because of unbalancing. So that's what you will determine. Then the bearing reaction can be measured. So since the part is rotating while measurements are taken, a stroboscope. I have personally used this equipment. I thought it's interesting to let you know. So stroboscope is used to indicate the location of the required correction. So what is stroboscope? From Google actually? It is an instrument for studying periodic motion or determining speed of rotation by shining a bright light at intervals so that the moving or rotating object appears stationary. So this light is a special kind of light actually, which flashes light at the same speed as the part is moving. It's a very interesting physics problem. So your part is moving with some certain frequency, and you are putting a light or flashing a light with the same frequency, so your part will look stationary because of that light. So this is the beauty of this machine, stroboscope. And you can now imagine, I will repeat again. So this flashes the light with the same frequency as the part is moving. So the frequency of part, or number of evolution of part, the frequency is the same as the flashing light. So this will help you to see as like the part is static. So if the part, if you want to see part is static, then you will find out where the inertia point is by marking on it something like that, and you could find it where the unbalanced loads are there. So for this one you can do, since the part is rotating while the measurements are taken, a stroboscope is used to indicate the location of the required correction. Because it's moving, if you don't use this stroboscope, you will not be able to find out the exact location where the part is there, where the unbalance is there. So for that you basically use this one of this equipment. All right. So when machine parts are manufactured in quantity, a balancer is required that will measure both the amount and location of unbalance and give the correction directly and quickly, right? So you can place on such component, on such one, there you can find out where the part. So these kind of components are placed within the manufacturing line. So you manufacture, you quickly see if it's a balance or not. You put another part, if you see it's a balance or not. So the balanced part will go through, and the unbalanced part you need some further attention only. Also, time can be saved if it is necessary to make part rotate. So for such component, this is one of the propellers sitting on one of the balancing machine. You place it and then you see if it's a static balance, if it's some wings are up or down, you will find out. So If some wings are up and down, then in that case it means it's not balanced. And in also worst case, you rotate it and then you also find if it's a balance or not. So this machine is essentially a pendulum that can tilt in any direction as shown in the figure, right? Yeah, so this one actually. So this is the schematic of the same diagram. So this one, so this is aircraft proper assembly balancer. So inside how it looks like, you place it, and then this actually, because of the weight, it will move this pendulum. So when it's inclined from the angle theta, you would be able to find out what level of unbalancing you have. So when an unbalanced specimen is mounted on the balancing machine, the pendulum tilts. The direction of the tilt gives the location of the unbalance, whereas the tilt angle theta indicates the magnitude of unbalance. You see, this is a very simple machine actually. You place propeller, you find out which direction is tilting. That's the direction where you have to consider the unbalance, and the angle which is basically measured. Because of this pendulum is tilting. This will help you how much is tilting, so that will help you to find out the magnitude of the unbalance. Some damping is employed to reduce oscillation of the pendulum. Yeah, so you can also provide some balancing, some damping, because you don't want your pendulum to have some kind of oscillations. If it does have, so it will contribute towards the unbalancing, which will invalidate your results. So you want to have this one as a this pendulum working in such way it does not have any oscillation. All right, now it's a dynamic balancing. So this figure shows a long rotor with distributed mass that is mounted in bearings at A and B. So A and B, these are the bearings. Suppose that two equal masses M1 and M2 are placed at opposite ends of rotor. So these two are, so suppose the two equal masses M1 and M2 are placed at the opposite side of the rotor. So one mass M1 is over here, M2 is over here, at equal distance R1 and R2. So this distance R1 from the center, this is distance R2, this is the mass. Since the masses are equal and an opposite side of rotational axis, placing the rotor on the rails as described in section demonstrate that it is statically balanced in all angular orientation. So because you have placed this M1 and M2 at equal distance R1 and R2, equal distance, and the masses are equal as well. So what does this mean? This rotor, which is supposed to be moved in this direction, is in static balance. What does this mean? You put them on a rail, on a rails as we did in the first experiment, and this will remain static balance. So it will find its neutral position because effect of this mass, which is causing some force, and is cancelling out by effect of this mass. So both are cancelling out each other basically. So they are called as a static balance. So the masses are equal on opposite sides of rotational axis, placing the rotor on a rail. Demonstrate that it is statically balanced in all angular orientation. So it will be balanced. If the rotor is placed in bearing and caused to rotate. So you see, this is a very good example where the part is in static balance. But now what you do, if the rotor is placed in a bearing, so these two bearings A and B, these two bearings, and caused to rotate at angular speed omega, then M1 and M2 create inertia forces of magnitude, this much magnitude, M1 R1 omega square, again inertia forces formula, mr omega square for mass 1, mr omega square for mass 2 respectively. This inertia force produces bearing forces Fa and Fe. So we have bearing forces Fa and Fe because of these inertia forces. So this one is causing outward force M1 R1 square, and this is M2 R2 omega square. So of course this will result in a bearing forces. So therefore a rotating part may be statically balanced and at the same time dynamically unbalanced. Very important consideration with this example. So if the part is in static balance, as we seen, because we have masses at equal masses at equal distance at different places, so they are causing it to cancel out and we have a static balance. But when it's rotating, then it's not a static balance. It is not in a dynamic. It's in dynamic situation, so it's not. It will be dynamic unbalanced. Why? Because of inertia forces of each mass causing outward forces, and which is continually causing Fa or Fb forces basically. So for a single mass system, 15.7a, both bearing reaction forces are in the same plane and in the same direction. For example, one of this mass, which is just one mass, Fa will be in this direction, Fb is in this direction. This is exactly the example we have given for the disc on a shaft. Therefore, the system is statically unbalanced. So because this mass now is just one side, so of course this is a static unbalanced situation, right? For two masses in figure this one, the static unbalance creates a couple tending to turn the shaft and over end. The shaft is in static equilibrium. So now, because what you have done, along with this mass, you have placed another mass, of course with the same radius, same equal mass, so you are causing an equal situation. So that's why the shaft is in static equilibrium. But the opposite couple performed by the bearing reaction, note the bearing reaction forces Fa and Fb are still in the same plane. However, they now act in opposite direction. So in this case, they could act in opposite direction. Therefore, the system is dynamically unbalanced. So note also the rotating mass system may be modeled as either a discrete or distributed system. Procedures for static, yeah. So basically, this is exactly the same thing which we have discussed over here. Thing is in static balance, so this is a static balance, but this is dynamic unbalance. So this is a static unbalance is shown over here. So in general case, accurate distribution of mass along the axis of part depends on the configuration of the part, but inaccuracies occur in machining and also in casting and in forging. So these are a list of some of the reasons why we can have those unbalance. I have briefly discussed. Once again, I'm putting it here, so just to make it good summary actually. All right, so the inaccuracies occur in machining and also in casting. So machining, casting, and in forging. Other errors or unbalances may be caused by improper boring. So you make a drill, or you have a key, you have to have keyways in a shaft to attach some other parts, and assembly. It is designer's responsibility to design a rotating part so that a line joining all mass centers is a straight line coinciding with the axis of rotation. So this is the designer responsibility. So design the rotating parts in such a way the line joining all the mass center is a straight line. So if they are not in a straight line, of course they are causing an unbalance. However, a perfect parts and perfect assemblies are seldom attained. Consequently, a line from one end of the part to the other joining all mass center usually spatial curve that may occasionally cross or coincide with the axis of rotation. So if all the masses are on one center, they are not away from the single shaft, then it will be called balance. But it is seldom achievable. So normally it is a spatial curve basically. What does it mean? It is in kind of space basically, right, with reference to this axis. So because of that, you will have the reasons of unbalancing basically. Before balancing, usually a part is usually out of balance both statically and dynamically. This is the most general kind of unbalance, and when the part is supported by two bearings, we can expect the magnitude as well as the direction of the rotating bearing reactions to be different. So we can find the reactions which will be of different. So these are some of the reasons which I have explained quite well in the beginning, uh, why we have the unbalance because of the manufacturing and assembly lines, and we have to correct those basically. So now onward we will do one of the method called graphic analysis. We will use this methodology to find out, or to balance actually, to find out what are the unbalanced forces. And of course, once you know unbalanced forces, then we will go how we can correct those. So for that, you will use these equations actually. A very famous equation for balancing: summation of forces must be zero, and summation of moment is must be zero as well. If you reach these two conditions, means you are on the balancing actually. So are used to determine the amounts and orientation. So you see, both things are really important. We need amounts and orientation of the corrections. We begin by noting that the magnitude of the inertia force mr omega square of an eccentric rotating mass is proportional to its mr product. So what is it? The magnitude of inertia. So we have seen the definition of mr. So mr omega square is basically inertia force of an eccentric rotating mass is proportional to mr. Yeah. So because all components are moving with same angular velocity, so mr is the one which will lead the way actually, because omega is same for everything. So mr is basically the eccentric rotating mass is proportional to mr product. So more eccentricity means more r, means mr product will be higher. Thus figure 1.58, vector quantities proportional to inertia forces of each of the three masses mr1, mr2, m2r2, m3r3. So for example, this is one of the system where you have mass m1, m2, m3, and their distances are r1. So r1 is in vector form. Remember this is r1 vector, this is r2 another vector, and this is r3. This is a distance and direction both. So this vector is giving you distance and direction both. So then the product is this one basically, m1 r1, m2 r2, and m3 r3. The first equation is, so this one, the F actually is applied by constructing force polygon. So when you do force analysis, you produce force polygon as shown in figure 1.15.8b. So this one, yeah, so this is the force, mr is a force, so this is the force polygon. Since this polygon requires vector mcrc, so this mcc stands for correction, right? For Collier, the magnitude of the correction mrc, and its orientation in parallel to vector mcrc. The three masses of a figure from 15.8 are assumed to be rotated in a single plane. So this is the correction for the case of static unbalance. So again, let me explain over here what is being discussed. So you got three masses, 1, 2, 3, and one, it has r distance and it has this magnitude. So m1 r1, this is the vector. What is this vector? This is the product of m and r1. So of course m is a static value, is a scalar value, so this will remain the same. So you have mr1. So this is the mr1 vector, this is mr2 vector, this is mr3 vector. Now what you do, so this is the vector, you draw a parallel vector over here. So this is the parallel vector over here, this is the same length and same direction, and then mr2, which is this one, right? So this is this one, and then m3r3, which is this one. So this is the direction and this is the length, the same. And then to connect both, because this polygon is required to be made, this one, which is mcrc. So you see, from here you can find out what should be the correction vector. So mc and rc both we can find from here. Yeah, so that what is explained over here. This is the force balance basically. So this is the one of the example. So the end view of shaft, you will have better idea from here when we solve this one. This is more like a theoretical example. So the end view of a shaft with mass m1, m2, m3. So this is the end view from one of the view from the one side actually. So you see this actually the shaft is like that. So you got a bearing, one here, a bearing here, b over here, and this is the length of the shaft. So LR is the length of the shaft. But when you see from the side, either side from A or B, you will see all masses like that. So each mass has some distance from the shaft, which is this one. So this is given, and it has particular length as well from reference from A. So this is the left correction plane, this is right correction plane. So this has a distance L1, this is L2, and this is L3. And now each mass has certain distance from the shaft as well, which can be seen from the side, right? From the side you see this one, right? So M1 R1 is this one, and this is the R1 is the length of this one, how far mass from the center, and then M2, then M3, right? So these three masses are there. Now you can imagine when we see from the front, you see everything in one plane, but actually they are not. From you see from the side, they are in different planes actually. That makes this balancing a little bit more complex, because if let's say they are in just one plane, then it's easy to solve. But if they are different plane, so you have to consider the plane direction as well. So radial distance R1, R2, R3 is shown, a side view of the shaft showing left and right correction planes, and axial distance L1, L2, L3 to the three masses as shown. Determine the magnitude and angular orientation of the corrections to be made on each correction plane. So now we have two planes where we want to correct. So this has certainly some unbalance because it has different masses, different radius. When it's rotating, then it's causing unbalance. Now how to balance it? We want some correction to be made on this plane and some correction to be made on this plane, on the left and right. All right, so applying this second equation, the sum of moments of inertia. So sum of moments of the inertia forces. So moment of inertia, for what is the moment of inertia force? So as I have told you, the force is basically mr1, right? This is the force. Actually the force is mr omega square. Inertia force formula is always mr omega square. Because omega is constant, so we just take mr, that's it. But actually omega r is omega r, mr omega square is a force. So we are not constraining omega. So this is called as the force balance when you do mr1, mr2 or mr3. The moment, how can you find the moment? Moment is always force into distance. So this force, if you multiply with the distance, this will give you moment. That's what we are doing here. So we are doing the moment analysis, so which is basically m1 r1, that is a force. You need to multiply with the distance, which is L1, to find out the moment, right? So you see this mr1, so this mr1, let's say this was in this side, so m1 r1, so m1 r1 is basically, yeah, so this is a force and it is acting on this much length. So this much length will give you how much moment you have. Same goes for the second one, and second mass, third mass, and the left side correction. Yeah, because when you take moment across A, so any forces on this plane will be zero, so moment is zero. So moment, because of this LR, the length, this is the right correction plane, this force which is unknown, so this we need to apply some force over here which is unknown, and the length is LR, we need to multiply with that. So that is giving us mr LR R basically. So that's the moment. So this is a vector equation in which the direction of vector can be drawn parallel respectively to vectors rj. Consequently, the moment polygon in figure 1.5c. So this is the moment polygon can be constructed. The closing vector MRIRLR gives the magnitude and orientation of the correction required for the right correction plane. So again, from the side view. So this view is now very important now. So this one is the vector which is M1. So I draw a parallel vector to this one. So this is a parallel vector M1 R1 L1. So this is a parallel vector. Now the second vector M2 R2, which is in this direction. So that's what I'm constructing. So this is the second vector, right? And then we got M3 R3. So same way we plot M3 R3. Now to construct a polygon, I need to connect these lines head to tail. So we got this one, which is MRLR, satisfying this equation because sum of all the vectors is 0. So what does it mean? They are all in one loop, in one polygon. So the resulting connecting is basically this one, right? So that's the one which is giving me. So the length and as well as the direction of this one will help us to find out what will be the correction on the left plane. Sorry, on the right. So this we are talking about right. So this is the right plane, right? So by using the moment balance we found for the right correction. All right. Now the next. So also the figure 1.5 called a moment polygon. It is worth noting that the vector making up this polygon consists of quantities proportional to the moment magnitude and are drawn in the position vector direction. A true moment polygon would require rotating this polygon 90 degrees. Yeah. So yeah, so this is very little point to be considered, which is important. So we are talking about this one as a moment polygon. So this is moment polygon, but moment is actually this one, which is a cross product. So L, which is in k direction, multiplied by MR, which is the product of those two vector. Whenever you take a cross product of two vector, the resultant is at 90 degree to those, right? So that's why we actually cannot say this moment polygon. Actually, we cannot say. Why? Because each moment is basically 90 degrees to original vectors, right? So for that reason, what is saying the best way would be to rotate this whole polygon 90 degree clockwise, right? So you rotate 90 degree, that will be actual polygon. But because this is not changing anything, right? So that's why we might not need to do that, which it will be very much clear in the next problems as well. So since each moment vector is properly expressed as this, so yeah. So again, because the moment is explained as this much, like this vector, it's a 90 degree. So that's why we need to be very careful when drawing the moment diagram. We call it as a polygon, moment polygon, but actually it needs to be rotated 90 degree. All right, now the first equation A, which is summation of forces, we apply. So initially we applied moment diagram, now we applying force diagram, the forces. So now we don't need to multiply with lengths. So we got M1, R1, M2, R2 and all those. So which is also similar phenomena over here. So we got the M1, R1, basically this is M1, R1, so just the direction. So this is direction and this is M2, R2 and then this is M3, R3. This is already determined, MR, R4. MR, R4 is already determined, this one. So you have to use this one basically. Now this is being used from the first part, MR, RR basically. So from here, what you have determined, you use that one. And then the resultant will be to complete the polygon. This will be the left side. Yeah. So this from this analysis we can find out, because this is the only unknown from this whole vector. From the whole equation you can find out basically, right? So both way, so by constructing the force polygon, the equation is solved for the left correction ML or L, so the left side basically. After solving for the MR or ML or L products, the separate quantities MR or R can be determined, since in general two of these magnitudes are specified in the problem statement and are chosen by the designer. So by this simple analysis you can find out. And in the polygon, one more thing I need to tell you, when you find out the resultant, the length is the magnitude and the direction is the orientation where you want to put the mass. So that's why you see here this has been drawn. So the right correction mass which is determined from the moment polygon is plotted over here. So this is MR into RR, and then on the left side the vector which is determined from the force which is in this direction is plotted over here. So this is plotted over here, MR, RR, ML basically. Thank you.